thank you very much for having me here, and it's an honor to be here. And I don't know where did you get out those words. It's too much honor than thank you. Anyway, my name is Xiao, and my talk today will be on the engineered bamboo structures, and talk about the research and the applications for geared for tall and larger spans buildings. It's really nice to be a next speaker to Orin and on those beautiful, architecturally beautiful structure. I'm a structural engineer. Always try to do those architectural part, but it's too difficult. So therefore, we decided to do just a boring, straight, laminated bamboo. So that's the start. So this is the contents of my discussions. Sorry, some of my slides will have some Chinese characters, but you can just look at the English. First, very briefly, an introduction about background, and then you can see this is the map of the bamboo forestry distribution, and it's basically well distributed, particularly in Latin America, Asia, and Africa. And fortunately, I was able to be on those three continents. Within China, there's several provinces well distributed, and so that's. But the attention to bamboo, now just like Orin said, this is kind of movement together with the push towards the sustainable development. So on the good things about bamboo really align with the United Nations. The goal of sustainable development goal for everything, including people's life, providing housing, improve the livelihood, reduce poverty, create a job on those things, on those good things. And this is some of the research we did a long time ago. One of the key areas is to reduce the carbon footprint, so I'll probably discuss a little more. And I'd like to, because as I mentioned, our work is mainly on engineered bamboo. So really our work is trying to how to replace or provide an alternative to modern timber structures. I'd like to give a very brief review about the timber structures. As the president mentioned, I was trained in Japan. My work was on steel and concrete composite structure. I'm still teaching steel structure and concrete structure. That's my long time, basically teaching career. But I did a lot of research. When I was in Japan, talking with Professor Garcia, at that time, Japan only allowed to build a two-story building, but later on they expanded that a lot. So this is the trend in the world about the tall buildings. Some are from Italy, London, this is from London, and then that's the one in Norway. And the current most tallest one is actually in Milwaukee, in the US, and that's stand for 86 meters. So there's really a competition about the tall buildings using timber, but mostly started from Scandinavian countries and also Canada. Canada is a leader, but now the US was able to come back to the picture, and this is this is a Milwaukee Bridge. That's the building and the currently the record. But certainly it's not just a pure timber, but with some concrete sheet walls and those things and the foundations. I took a trip to Japan, I think 2 years ago. I was able to basically travel from Tokyo all the way to Sao Paulo and to try to look at the current tall buildings in Japan using timber. Mostly are mixed structure. The timber and the concrete, or timber with steel. Many of the buildings I visited, they claim they were the first in certain way. For example, this is the hotel I stayed in Sao Paulo. It's the first mix the building with concrete and steel and everything. So, but this particular building in Sendai, just across the street from Sendai Station, is Japan's first 7-story building, pure timber. So that's and then there's some other buildings are first of certain things. So that's what happened in Japan now. And the Japanese are planning to actually finish the building of a 350 meter tall buildings, basically super spider in Tokyo. You know, Tokyo is a very active real estate area, and so that's okay. But the most interesting thing is they gave the contract on the steel connection contract to a small factory in China, which is not too far away from our lab. So they're doing some. They already started to manufacture the connectors for some other lower story, like a 10-story for that company. I think it's with the forest industry, something like that. And back to China, this is the newest building that built in China, and the very long arched building. And this is so far the 99-meter arch bridge designed by a group in Nanjing. And but most of the timber used are imported woods. That structure used the German Austrian wood, and this one I think is a Canadian SPF or something like that. Okay, so that's the trend in timber structure. In my view, as a structural engineer, so I think the current, maybe the tallest academic and engineering challenge, the most important challenge or most advanced research in academic research in structural engineering, not really in steel, not really in concrete. I mean, this is already done, but really is in timber structures, high-rise building, larger span structure. So that's my belief now. So then that's basically we're trying to follow that trend, like using bamboo. So that's really what we're doing. So first one, let me just give you a few shots about because Base has done a lot of excellent work using ground bamboo structure. 10 years ago, we also had the opportunity to work with INMAR, actually, a group of people also associated with INMAR, and build and also researched on a small building using ground bamboo, and coupled with a solar panel on the top. So that's the building we built, just a single story, and so it looked like something, but instead of using the chicken wire and those steel screen, we used plank bamboo for the sheathing panels. And there's also some sort of, we also used some of the poles as a conductor for the heat. And we did some lateral loading test. This is just a monatomic test and a cyclic test and those things. And also the roof. And the paper was published in 2 years ago, Structures Journal. And most of our existing research, about 20 years research, are summarized in my book, in Engineering Bamboo Structures. If you're interested, it's available. So when I go back, I will make sure we send one copy to Base. And I just want to very briefly just mention some of our very recent research. We're more interested in looking at some microscopic, because I have a few PhD, they need to write papers, they need to do some newer research. We also have a robot available in our department, so we were able to use that to build some of the domes. And also, this research was a little bit interesting because we built a building in a very cold region. That was So why not do some lower temperature test? So we did something, and you can see this is at a very low, not really. Maybe this is good for something in the satellite. Because recently I read a paper, a Japanese launched a satellite using bamboo, not bamboo, timber. But maybe next one you launch something with bamboo. So those the high altitude you probably need some lower temperature. But you can see it's very brittle. And another research related to your work is that we did do some nail laminated bamboo because glue laminated it's a little bit we use too much chemicals. Again, it's also more expensive. So we decided to do some nail laminated bamboo girders and flooring, and we had a couple of publications. This is just a favorite patterns. We look at the different, like this kind of connection with the top, and then just a straight butt connection. But the different layers, we try to laminate the different layers together, and also compare with timber layers. This is our ongoing research at the moment. It's using this Austrian shotgun, and I'm not sure, probably not a Huey, but we can shoot this. Sorry, maybe related to Huey. And we're using this kind of hardwood nail. I think the company called ECP or something like that. So we use this, try to do the lamination, but it's a little bit. It's no problem for timber. However, for the laminated bamboo, it's a little bit harder. If it's thin, it's okay, but for 30 millimeter thickness, you have to do some pre-drilling. We tried a different diameter of different drilling. It's just a little bit smaller than the nail itself was able to do something, and we did the straw testing and also shear connection test shown here. So we're just summarizing the result. It's also interesting because in the manual of the manufacturer, they said, oh, we do the shotgun kind of shoot the nail into the wood because of the high speed. Then there's resistance. Then there's the same how the timber welding, wood welding, because it's high temperature, generate heat, then they melt things together. So we actually observed something and then look at this on a microscopic picture. To me, we don't know too much, but just look at something. It doesn't have a little bit of that kind of wood welding effect. And so this is some test result, and some of the curves. This visual curves and shear curves. And the shear curve is a little bit similar to the timber nail, the steel nail. One of my students also trying to do something to look at the fiber bundles of the bamboo, and then later on, then just by looking at some of this kind of scope. The technology, because we have a biomedical school nearby, so we use some of the high-tech equipment, just have to pay a little money, and then also try to do. So basically what she was able to do is to look at the bamboo by bundle strands, then by scan a section, by counting for how many bamboo bundles divided into different areas, then to connect with the bundle testing, then we're able to somehow to get the strength of this string. So that's hopefully is something better. So this is also the test we are doing is the fire testing, and this is just we're just starting now, and we have about 30 columns to test. So this is it's actually a pretty big column, 1 meter tall, 1.5 meter tall, and section size is about there is 180 by 180. So basically, the first phase we look at the residue strength after burning for 30 minutes or 6 minutes, and then to look at the residue strength, just exploding test. And then we also, next step is to look at the different way to do the fire protection. So this is some of the test results, and this is the fire curve. Okay, so with that, just report to some very recent research. And now I'm going to switch out to discuss, to show you some practice we just recently finished. And these are some photos of the buildings we completed in last 20 years. And a few interesting things. This is one of the bridge we built that also got some award. This is a building, not this building, we built a building on the campus where President Obama's father went to university, and his grandmother was living nearby. I was able to visit his grandmother, and actually President Obama was very close to this lady. You can see, I'm not sure, I think this is Juan Francisco. Some of the other buildings we built. So some of the patents we got. So first project, actually we designed a project for Taohuajiang Bamboo Company. I think this company is one of the major bamboo manufacturers, a three-story building, but we did not participate in later on manufacture. So the building should get something like this. So basically it's a free building. We added steel bracing for the tribute for that work. And this is some of the details. The next building is basically this is a 7-story tall mass bamboo building, which is a small building in terms of capital area. It's just 120 square meters each floor. And totally it's basically 6th floor, but with the penthouse. Totally is a 7-story. The total height is 20.3 meters. It's used as a research facility and office. It's in our lab in Ninhai, which is a port city, one of the major port city in China, and also probably largest, one of the top 10 in the world. So this is what the building looks like. And I'd like to acknowledge my student, this Xiao, who is currently in UK, just switched the location from Newcastle to Imperial College. So she was really, sometimes when you do research, you really have to have a really good student. She's the one that really endured the hardness for design and calculation and testing and also construction management. I'll show you a picture. This is what she was directing crane to lift the beams of the buildings. Really very dynamic young lady. Some of the calculations. So basically, we follow the regular building, but this building was not really true building. It's a really illegal building. But as I which is built on the government land, just the same. We're doing research. If you really need it, we just tear it down. Still tear down buildings as research, another paper, so that's fine. So basically, it's but the calculation, some examples are just that's the laminated bamboo. But we actually use the two types of laminated bamboo. Inside, we call it a thinner layer, the blue bamboo, and the outside is a thicker layer, which is like the one they use to build flooring. But the inner one is maybe used for formworks or the flooring for containers. So, but the inner one is really cheap, but it's a two-dimensional, and it's actually more stronger in terms of, but the surface is not as good looking as the singular ones. This is some of the connections. We basically did everything following the timber code. We're using our research testing result. And Xiao testing, we have this frame, self-developed frame. It's a bit different than yours. So the key difference, when you say, so the top is fixed, the bottom is moving. So because we're trying to do tall buildings, each floor, the most, maybe the critical cases really double shear. But if it's a single story, it's really cantilever. So that's why we are trying to create a double shear with double bending, with point of inflection in the middle. So this is actually it's a new design. So we did a lot of testing and also with this freezing and with our testing result. And I'm not going into details, just to show you that. So basically, this is a trim shear wall. And also we tried with the timber studs, we put the studs on both sides. So you look at one of the paper published by UBC Professor Lam, his group, that we put the stud on two sides stronger. It is true. So my student also published paper because these days we have to do something with AI or machine learning. So she was able to use OpenSea and develop the machine learning modeling with 35 parameters. Totally non-practical, but able to publish paper. So basically using that model, but that's for language shear wall, but then we combine with this is just recent paper, then we combine that model for the free shear wall. And so this is a comparison with the test result in blue and the modeling result with the orange. That's it. So basically, then we use the result and things everything okay. We design the building. These are the systems. In the shorter direction, we put the bracing in these two spots, one each. And in this longer direction, we use the shear walls, the framed shear wall system. And in terms of earthquake, the wind and the earthquake. For earthquake, for example, in this direction, the inertial load will be distributed on the floors, then transfer to the shear wall on both sides. So that's the system. And also wind will be blowing to the surface, then burned by the wind, and also again transfer to the side to resist the that load. So that's a system. Then with that kind of mechanism, we did the design a little bit different. So this is the wind load. For wind load, we designed it for like a 7-story. But for earthquake load, actually we designed the structure. It's not a really seismic area, but we designed the seismic load for 8-story. Because we also put a water tank on top. The water tank itself can contain water equivalent to the mass of a 2-story, just for possibly future analysis and instrumentation. Okay, so with that, both of the wind load and the earthquake load satisfy the limitation by the parent code in China and also in the US code too. And then we entered into detailing design, and after the member calculations, there are all the members. I think architects probably have this kind of explosion drawing. I think it's called. So you look at each elements, so on the elements here. Then we entered into manufacturing phase, and everything is manufactured in our own lab. We were able to develop our own compressors. But again, our compressors only compress do the cold lamination, but the board was manufactured by the manufacturer. I think someone may know it used to be called Dizu or Dizu Huizu. It's in Jiangxi province, one of the very good manufacturer, manufacturer, been working with them for a long time. Then all we need to do just take the bamboo board and then we coat that. It's really, our process is just like the lamination process for glulam, for timber. And also for selected elements, we did the checking about the strength. One of the most important, the strength is really not an issue for timber, for this building, but it really is after the lamination, whether you can maintain, whether the elements can have the required stiffness, the modulus, and then we did the non-destructive testing to get it calculated. And selected slabs, so we also use the so-called CLBT, cross-laminated bamboo and timber. It's a word that I created, just like a blue lamp. So we just so basically it's completed. So we did the construction for every two-story as a module. So we basically using so-called balloon and platform construction for timber. So basically we use a balloon frame, each two-story, then we can create a two platform then to work on the further floors. So for just for the framing, each of this two-story can be completed in 3 days. So therefore we can just, we really tried, but it did not work. We tried to rent the crane just for 1 day, but later have to rent for 2.5 days. So basically just 1 day. So initially we tried to lift the frame at the we thought it's more efficient, but then it turned out to be more difficult to line this connection. So it's really hard. So eventually we decided to just lift each individual part instead of beams, so that's more, actually turned out to be more efficient. Very quickly, maybe just some movie, and we can see. This is a movie that I like to create. Might be your, should transfer to you, or some directly just the lamination of the timber and the tagging. And so with this project, we were able to establish our own whole manufacturing capability. So once we finish it, we do the fireworks. And you can see in winter, we cannot do other things for the now. Okay, and then with this, the next step is we try to do a lot of health monitoring, and we did do some instrumentation, and we use the digital twins. Unless a newer buzzword to me, I'm more traditional than my students are modern versus English, so you have to track the students. So these are the Professor Kassi talking much better about it. So if you're interested in instruments building together, so anyway, so the work of vibration. Then the preliminary CO2 estimation, eventually we can reduce the CO2 by, I think it's over at least half comparing to conventional concrete. By the way, we did use some of the recycled concrete. This old factory, we tear down some old factory building, we reuse the blocks just to hide into the foundation. So probably reduce a few tons of CO2. Okay, so this is luckily we recently got award some very pleased got award by the Architecture Engineering Institute within ASCE American Society of Civil Engineers. So listed something like that. So we actually got one major award with three other smaller awards. And we currently actually waiting for typhoon, just wait for another typhoon. You guys generally here in Philippines. Last year we had some mist. Okay. So our next step is we will use this building as a platform for international collaboration for many other things like the vibration, acoustic, thermal, and many other interesting research hopefully. Another building is actually a commercial building. It was really created. It's a building in the nearby. It's architecture design or something like that. It's a 2,000 square meter, a two-story building. It's a conference, community center in a larger development. It looks like here it's by 3 span in this direction, 5 span in the other direction. Each of the span is 8.1 meters square. Somehow in our discussion with the engineer, I told them I will build a bridge 10 meter long before. So probably it's not amazing if you just do another building shortest. So they decided to take up one hall. So in here, each of the span become 16.2 meters. That creates a lot of challenge. The good story is that initially the building was designed by steel, and the local government people said, why don't you go to talk with the engineers, owners, and try to sell some timber or bamboo. But they said, oh, we could do the timber. Just recently, another timber similar building got award. One timber. I said, timber, we use Canada imported wood, what's good. That's a lot for CO2 during transport. I said, if you would do something with bamboo, would be the world first. I was able to convince them. So anyway, finally, I got the design and the manufacture contract. So myself, able to spin off the serve as a manufacturer to supply the bamboo components, and then we have, but it's really a lot of trouble to do a real construction job. And the structure system, anyway, it's relatively simple. It's a frame, but with a bracing for the lateral load. Several interesting things. It's probably the first large-scale engineered mass bamboo building with official approval. And the public building load. The building load was quite high. So we also put the thermal panels on top. And also for the first floor we used the CLBT floors, and for the roof we call it the twisted. It's basically laterally laminated along but because it's a curved roof, you have to twist it one by one to generate the curved floor. So this is CLBT, and we do the lamination for the roof. And this is where we manufacture. We borrowed a workshop to manufacture our component. This is the pressure we have homemade with a 16-meter just specifically for this building. Okay, this is 16. So this is the 15-meter long, 30 millimeter thick bamboo plate, the board. That factory was just before this one. We were thinking to use a connector for that 16 meter. But then luckily they made a new machine that's able to produce 15 meter long board. Then we were the first one bought the product, then made the 16-meter long board, so you can see the buildings of that. Once finished, this one is a 94 centimeters tall. I think it's 240 millimeter wide, 16 meter long. One of the good things with working with them is because this is so large, they slip here for dimension to be too deep. It's very difficult to make the machine. I will need to either just take this portion, we just did not apply glue to it, put something inside the later on. Once we finish the lamination, we just take it off and become a slot. Then we do the tubing, everything to get the dimensions done. And again, for this kind of a rear laminated, how to guarantee the stiffness, modulus, to be the same or higher than what we use in calculation is really the key point. So we did also non-destructive testing and some work. And then we also do not really trust non-destructive testing. Made a frame, then just add the pure damping moment to that, and then actually measure the string, then calculate the E divided by I, the modulus of the elasticity, which is higher than what we use at the scene. So that comes to that. This is during construction, different steps. And it's the last step here. You see, this is a 16-meter long with the overhead. Then we put the other side, the powerful lens, we put a steel joint here, very heavy steel joints, connectors here. So powerful lens for lifting is 27 meters. We lift by 2 feet at the same time. So those are 7 girders for those 2 spots. And so then we put the top floors and there's a lot of modifications, and then at the end, the architect decided to half a circle to do some, to make it to be like a tree. So, something a lot of those interesting work. And some of the monitors were doing the construction, not really So another thing we're working with one of the experts at the University of Illinois, trying to do some wind instrumentation. And he was able to get and make a very complicated, amazing wind model to look at the wind stuff. I think it might be some problem during the type season. There's the pressure and the roof. Quickly. So last year we missed the one typhoon. We were really numerously waiting with the eventually went to Japan. We really very numerously waiting for this year. So then my conclusion. So basically based on our research in the community for the last 50 years, I think that we could engineer that are ready to be really used in natural structures, and it shows good potential to be sort of one alternative to existing materials, and hopefully that's the solution. And this is the site that looked like at the beginning. Then this is about time we have another renovating this building, but just partially. Basically, the office. I'm looking forward for our collaborations in the future. Not only design, but hopefully something like that. With that,
thank you very much, can promise you